6.5, we are on to the third transformation. In 6.3, we did translations. In 6.4, we did reflections. And now in 6.5, we're doing rotations, the third of four transformations that we're going to be looking at. So what is a rotation? We all probably have a pretty good idea of what a rotation is, but let's define it. Note card 207, a rotation is a transformation that turns every point of a pre-image through a specified angle and direction about a fixed point. That's a lot of mathematical geometric jargon. Basically, we're going to have a fixed point that we're rotating around or about in an angle of rotation. So pause me, write down this definition, and draw this picture as well. Try to draw it as good as you can. Make sure you have the A prime, the B prime, the C prime, the little primes on there, that it's 90 degrees, pre-image, image, and the fixed point is P. Pause me, finish it up. Now, like I said earlier, we're going to have to describe these rotations, and you need to know what that fixed point is, and you need to know the angle of the rotation. So again, a rotation occurs when an object is turned around a fixed point. To describe it, you've got to know the angle of rotation. For example, a half turn is 180 degrees, a quarter turn is 90 degrees, three-quarter turn 270 degrees. And you're also going to have to know the direction of the rotation. We can go clockwise, like if we're reading a clock this way, or counterclockwise, backwards. It's also called anti-clockwise. And then the center of the rotation, this is a fixed point. Oh, there we go. This is the fixed point about which object moves. And guys, just so you know, in math 2, that fixed point is going to be the origin. We're going to be rotating around the origin. It can get really tricky and messy and wonky when you don't rotate around the origin, but that's what we're going to be doing, and that's the only type of rotating that we're going to be doing. Pause me and finish up note card 208. This is just another talking again about the center of rotation, this fixed point. This is not a note card, but I just wanted to say that this is the center of rotation, that fixed point that you are rotating around. Angle of rotation, this is 90 degrees. Now this is 90 degrees counterclockwise. That's not how you would read a clock, so that's counterclockwise. Now tell whether each transformation appears to be a rotation. This one does not. This one is just a slide. It's a translation. This one, yes, our fixed point is right here, and we are rotating this way, counterclockwise. Rotational symmetry, just want to throw this in here real quick, is in a figure in a plane, so a flat figure, has rotational symmetry if the figure can be mapped onto itself by a rotation of 180 degrees or less. You know what? I am going to make this a note card. Hold on. Yeah, I decided I did want to make that a note card because that is fairly important to know if something has rotational symmetry. And so this is note card 209. Go ahead and write this definition down. And you don't have to draw those pictures, but just have that written down. Pause me and finish up note card 209. Now let's look at some examples of whether or not something has rotational symmetry. So does the figure have rotational symmetry? If so, describe the rotations that map the figure onto itself. So this blue rectangle, does it have rotational symmetry? Now remember, something has rotational symmetry if it can be mapped onto itself by a rotation of 180 degrees or less. Now we're not talking about a fixed point rotation. This is kind of like a segue away from what I was just talking about. That we're gonna come back around, okay, to the fixed point symmetry. But like this one has rotational symmetry, right? Now, will a rectangle map itself back onto itself? Yeah, after 180 degree rotation. A 90 degree rotation, no, but 180 degree rotation, yes. Now, what about B, this regular hexagon? Absolutely. The regular hexagon has several ways that it'll map right back onto itself. Now, that trapezoid, no, that is not going to map back onto itself within 180 degrees. Now, 360 degrees it will, but that's not the definition of rotational symmetry. All right, does this have rotational symmetry? No. It would have to take a full 360 to get there, and it needs to do it within 180 degrees, so no. But this one, yes, 180 degrees would map it right back to itself. What about this one? Yes, 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 several times. All right.